So for the Unit 5 all or nothing quiz, so this is with orbits and stuff. So starting with the problem right after that. So for the part A, you need to find the total mechanical energy of the spacecraft, assuming the gravitational potential energy is zero at the infinite distance from Earth. So you know that the energy of total is equal to the energy of the kinetic energy plus the energy from gravity. So, which equates to 1/2 mv squared minus the gravitational equation, which is big G m1 m2 over r. And then, so after you plug in each of these, you're going to end up with 1/2 times 1,000, which is the mass of the spacecraft, times 7.1 times 10 to the third, which is the velocity, or the magnitude of velocity for the spacecraft, subtracted from big G times the two masses, so 1,000 times, which is the spacecraft, times the Earth, so that's the 6 times 10 to the 24th, all over 1.2 times 10 to the 7th, which is the radius of the spacecraft from the Earth. And so after you solve that, you get E equals negative 8.1 times 10 to the 9th joules. Alright, so for part B, you're trying to find the angular momentum. So you start with L equals mRV, or L equals mRV. And so, pretty simple. It's 1,000 for the mass of the spacecraft times the velocity of the spacecraft, which is 7.1 times 10 to the third, times 1.2 times 10 to the 7th, which is the radius, and all that ends up equaling 8.5 times 10 to the 13th kilogram meters squared per second. Alright, so now for the part C, we're trying to find the speed of the spacecraft at point B, which is all the way out here. So you know that momentum is conserved during this, angular momentum is conserved. So you know that mRV from the initial is equal to mRV for the final. And you know that the m's will cancel because it's the same mass. So then you're left with the 7.1 times 10 to the third, which is the velocity, times the 1.2 times 10 to the 7th radius, equal to the velocity you're solving for times 3.6 times 10 to the 7th, which is the distance from the center of the Earth here. After you just isolate V2, and V2 ends up equaling 2.4 times 10 to the third meters per second. Alright, so then for part D, you know that we're solving for the speed of the spacecraft in its circular orbit. So because it's in a circular orbit, you have mv squared over r. And so that is set equal to the gravitational one, so m1, m2 over r squared. So the two r's on the bottom cancel. m1 cancels. So you're left with v2 equals g m2 over r. And so after you can just plug in numbers here and take the square root. So you have v equals the square root of gm2 over r. And so now you just solve for v, and v equals 5.8 times 10 to the third meters per second. And finally, so for E, you're trying to find the minimum speed of the spacecraft at point A for it to escape, or sorry, use an escape velocity. So you know that energy, the total energy will equal the total energy after. So you know that the kinetic energy plus the energy from the gravity will equal the force of gravity times the acceleration And so that's going to be infinity, because it's moving farther and farther away, which ends up equaling 0. So then what you're left with is 1 half mv squared plus negative g m1 m2 over r equals 0. So because it's 0 here, you can move the gravitational equation over to the other side and set them equal to one another. In addition to that, the two m's will cancel out. So you're left with, before you move it over, with 1 half mv squared, or just v squared, equals g m2 over r. And then you multiply by 2 over here and square root, so you're left with g equals the square root of 2g m2 over r. And then after plugging in everything from up here, you're left with v equals 8.2 times 10 to the third meters per second. All right, so now we're going to go over some of the basic notes from the chapter.
Oh, where we start? Over here. All right. So, one of the early important things to understand with this is that essentially we're going to be talking a lot about momentum and impulse. And impulse is force times delta t, or the integral of force dt, and it's essentially your change in momentum. Once again, momentum is rho v, mass times velocity. And so the important thing to remember about momentum is that momentum is always conserved, so you'll always have the same momentum. So when we look at, let's look at angular momentum, which is which as we said earlier is MERV, or I omega, and so angular momentum, just like normal linear momentum, is always conserved. So whenever you are using a problem with angular momentum, you can always set your final angular momentum to your original angular momentum. Also, torque is the derivative of your angular momentum, or I alpha, and of course, when the net torque is 0, L1 equals L2, because you're not applying any force to the system of changing the momentum. And then the other thing that's important from this unit is the rotational kinematics, which use this weird form, a cosine omega t plus phi. That's your displacement. And then your acceleration is negative omega squared a cosine omega t plus phi. So it's essentially x of t times omega squared. Velocity is also r omega, and so you can use these equations to solve a lot of the issues in angular. It essentially acts as angular analogs to the normal kinetic equations. And then with gravity specifically, it's important to remember that the gravity constant g is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, and that gravitational energy is negative gm1 m2 over r. So that's another important one, because you will be conserving energy in all of these problems. And another useful formula can be, if you're looking for escape speed, it will always be v equals the square root of 2gm over r. All right, and I think that covers pretty much most of it.